Okay, let's get started for getting into the last block of the day. And we have just the right amount of time left, I think. So we end at 4:45. That's what we're aiming for. So you saw them from what we talked about before the break, that right now, what I was talking about are some fundamental matters of this kind of analysis, blended with some specific matters of how Mplus version 8.0 is functioning right now. So that became a little bit entangled towards the end, but know that these things are being worked on all the time, and I'm sure next time we teach this, this is going to be more intuitive in that area without question marks. But we're going to try to focus on the lasting important characteristics here. So let's go forward in this analysis, the two-level analysis of the kind that Ellen also did. Runtime was 3.54, there you have it. And here we saw the results. I just wanted to point out a couple of new output warnings that we get. This is from this run, and there are three things that come out. 1, 2, 3. First comes a warning that says one or more individual level variables have no variation within a cluster. Variation, a cluster here is subject, right? So it says that the variable urge, the smoking urge, does not vary within the cluster. That is, it does not vary across time for some clusters. So somebody may say, I have smoking urge 0 throughout all time points. I have smoking urge 10 throughout all time points. And that's an interesting matter, because I think we need to think long and hard about how to model that feature if there are a lot of clusters, a lot of subjects who has that event of no within variation. It has a little bit to do with the floor and ceiling effects that we talked about yesterday, and censored or two-part modeling. And actually tomorrow afternoon at the very end, I'm going to talk about one little idea that may lead us to a better future in terms of being able to model this. But we notice, for instance, that subject 160 has this problem, or this issue. Maybe it's not a problem, it's a feature, and that's how the data are, and we should try to match it with the right model. So right now, we're not sure we have the right model. And then we get a warning in the standardization that Ellen described, in the computation of standardized estimates for that's cluster standardization, that is within person standardization. We have problems computing the standardized values, most likely due to autoregressive coefficients greater than 1, or parameters giving non-stationary values. Such posterior draws are removed. So that's just draws, meaning iterations here. The standardized estimates are produced in each of these iterations just like the raw estimates are, so that you get a distribution for the standardized estimates just like you do for the raw estimates. So in some of those draws, we weren't able to compute the standardized estimates. And you see, once again, it happened for individual 160 here. So you may want to go back to the data there and take a look at, was it correctly coded, and if so, what should we do? We get it also for subject 115, and if you look down here then for the third output, cluster 115 happens again. You may want to circle that and connect it to the 115 here. The last part is a part of the output that concerns the factor score comparisons on the between level. So the random effect values. Our input that gave us that was this FS comparison. When you say FS comparison here on slide 51 in the output, you get this output. So what you get is the factor score values ranked by size. So the biggest size is this one for cluster 115, and then it goes down for other clusters. Sometimes, so this value, 0.941, is pretty high for subject 115. which means that in some of the iterations for the standardization, it may go bigger than 1, which doesn't make sense. You can't have AR regression coefficients greater than 1. So that's probably why 115 has a problem there. These values, particularly for phi, or phi, the factor score, can sometimes be 1 or over 1, indicating that this model may not be correctly specified. So this is 3 good things to take seriously and think about. Here's a 4th thing. Time interval comes back into the picture. So for these data, these are the smoking data, I chose 0.08, and it gives a warning: the value specified in the t-interval option may be too big. You have a discrepancy between the actual time and the time recoded by the t-interval option, which is 9.517 in cluster 33. So subject 33 has this problem. It's only one cluster out of 250, so maybe it doesn't matter too much. But let's see what it means. What is 9.5? What does that mean? Well, then we have to think about 0.08, the t-interval value, the bin, the delta, corresponds to 2 hours. In this run, 0.08 is represented as one time unit in the analysis. Therefore, 9.517 corresponds to 9.517 times 2, the 2 hours, the time unit, which means 19 hours displacement. So the recorded time and the observed time and the recorded time differ by 19 hours. So that's a very large difference. So you may want to do something about it. The data for cluster subject 33 should therefore be inspected, and it turns out that the first 30 observations were made in less than a 2-day span. Which is strange, because the aim was to have only 5 random measures per day, so 10 for 2 days, and this person has 30. So what happened there? Maybe a coding error of some sort. So that's very informative too, and that value is high, particularly when it's high for many clusters. I didn't do anything about it. Which, by the way, I should say that the examples I'm talking about should not be taken totally seriously, substantively. They're for illustration. I tried to give you an example that's realistic enough so that your associations will be stimulated. The data that you're going to work with and analyze much more carefully. And nothing that I tentatively conclude here should be taken at heart. Maybe we could change 0.08 down to 0.04 and look at 1 hour distances instead. And then we could perhaps avoid this problem. You could try doing that, for instance. Now, checking the sensitivity to t-interval choices also can be done in the following way. You have, in a univariate analysis of urge on urge ampersand 1 at the previous time point, in the case of a non-random phi, and only the mean being random for simplicity, so a lag1 model, I played around with time intervals 0.08, 0.06, 0.04, and I found the autoregressive or autocorrelation, same thing, varying this way. Of course, the autocorrelation increases the closer the time points that you consider. But it should increase in a very specific way if an AR1 model holds. The phi with the interval t, say 0.04 here, should result in phi squared for interval 2t, 0.08. So squaring this should be equal to that. But squaring this is less than 0.15, so it's certainly not equal to that. And therefore, a pure AR1 model does not hold, which is true actually for these data. Lag 2 is actually significant. That's one of the misspecifications that I have made here with the aim of keeping things simple. Smaller time intervals can give more missing data. And then you see this here. The coverage that comes out for time is 40%, 30%, 20%. So smaller coverage for smaller time intervals, more precise binning. When it comes to time, though, and missing data, TMR recommends other values than we recommended yesterday. It's a totally different situation. 10 to 15% coverage is good, he says, and coverage as low as 5% is okay in his simulation studies. He'll talk about that tomorrow. Now, smaller time interval, so this is something that comes out in the output. Smaller time interval, though, gives longer runtime. You can see how this almost doubles in time, 22 to 40 seconds. It doesn't matter if it's seconds, but if that is 22 hours, and this is 40 hours, you may hesitate. And now we do a technical interlude here. Somehow this is very musically oriented with preludes and interludes. So we're going to talk about ampersands versus hats, because I thought that was a funny title. Where should the autocorrelation be applied? Here's what we talked about now, autocorrelation between y on yt minus 1. You see that in the literature quite often, perhaps in the econometric literature. They put the autocorrelation here. They're mainly, nevertheless. But this is also very common. You put the autocorrelation for the residual, like we talked about earlier. And I think, for instance, in many programs or many modeling efforts, you put the autocorrelation for the residual. And we are working towards doing that. TMR has done some work already. I actually have a developmental version of Mplus where I compare these two approaches. So we have the regular autocorrelation and the new residual autocorrelation. The regular, once again, urge on negative affect, that's the contemporaneous regression. And here you have the urge on urge ampersand 1. Regular, this is the total, albeit latent variable decomposed urge. Here you do the residual of urge regressed on urge 1. And we say urge hat on urge hat 1 with lag 1. So that's this thing down here. That is the hat notation, and this up here is the ampersand notation. Because in many writings, this is what people are interested in. So for instance, you may be interested in a regression of urge on negative affect in time series data, and all you want to do is make sure that the residuals, that you don't assume that the residuals are uncorrelated across time, but they have a autoregressive correlation across time. So if you compare those two models, you can compare them with respect to the deviance information criterion, the DIC, for the regular AR and the residual AR. Like for BIC, DIC should be, a good DIC is a low DIC. So this is worse than that. So you would actually choose the model that we've been talking about for this data set under this specification, which again may be the wrong specification. But I'm just saying that DIC is potentially useful for comparing models, although it has difficulties, mainly stemming from PD, which is in the 10,000s, which is the so-called effective number of parameters. It's not the regular number of parameters, because it includes also latent variables and missing data for each person as parameters. And therefore, the models has to be comparable with respect to latent variables and missing data. This, too, is a topic that we're tackling, TMR is keen on tackling, to make DIC more easily usable for comparing a larger variety of models. Getting the DIC value to a good precision is hard as well. It requires a large number of iterations. So for instance, if the parameter estimates converge after 5,000 iterations, you may need 20,000 for the DIC. And right now it's only available for continuous outcomes. So there's a lot to be done, but we've done an awful lot, and we wanted to get us started on this march towards more interesting analysis. So now we're going to get into a whole new topic that we haven't talked about at all before. And this is where the excitement starts, I think. So cross-classified analysis, so we just go through the bullets here. That has two between-level cluster variables, subject and time. Cross-classified analysis, in multi-level settings, deal with clusters that are not nested, like neighborhoods and schools. they're cross-classed. In that setting, you usually have several observations in the cross. Here we have only one. One observation for a given subject at a given time point. But the idea of using cross-classified analysis for longitudinal data is an old one. You can read about it, for instance, in Hugh Parkes' multi-level analysis book. So what we do is we generalize the two-level model to a cross-classified model. So for a simple case of random intercept, we can write the two-level model as y for individual I and time point t equal to a level parameter and a random variation over subjects around that level parameter. And then you have the regression slope on, in this case, the within latent variable centered part of the variable. And you add then a residual. So this is within subject variation. You can think of it across time. And this is between subject variation, characterized by subscript I only, not I and t, like we have here. The cross-classified model adds this part. This part is new. It says alpha sub t. So it's a random effect, just like alpha sub I, but unlike alpha sub I, it varies across time, not subject. Like alpha sub I, it has a mean of 0. So you can imagine that, for instance, early time points can have a high positive alpha value. Late time points may have a high negative alpha value, which would then be helpful, right, for describing a trend that goes down. But the average is 0, which I sometimes forget. Now, why don't we do this model all the time then if it's more general? Well, you have to pay a price. The Bayes algorithm is considerably more complex and very much slower, as you saw in those timing examples. Now, timings are also something that's not fundamental. There's a lot of intriguing possibilities to speed things up, which also will happen someday. So here's an example of cross-classified analysis. I call it a quick way to spot a trend in a variable. Trend analysis is done in many different ways in time series analysis for n equals 1. You do differencing and the like on the data, but here we model it. So what you see here is a cluster variable, cluster specification that has subject and time. That's time since starting to try to quit, in this case. So two cluster variables that sit up in the names equal list. T interval is the same. Analysis type is now different, cross-classified, random. Estimator still Bayes, processor still 2, B iteration still, in this case, 1000. And now we have within, between subject, and between time. So here we have, for simplicity, a fixed autoregressive relationship. And then we have a variance component for the intercept varying across subject and varying across time. So this is alpha sub I. It's actually the variance of alpha sub I. And this is the variance of alpha sub t on the previous slide. Once again, we ask for factors for urge. And you can make the factor estimation more or less precise. This has to do with how many draws, how many iterations you use for these unknowns. There's a longer story behind that, but I'm not going there right now. And then you can do a so-called time series plot, which I think is one of the more exciting plots in the new Mplus. Time series plots are used for the observed data that we looked at for each individual, but it can also be used to plot factor scores, particularly with cross-classified analysis. So on the x-axis is time. On the y-axis is this alpha sub t, which we refer to as between level 2a underscore urge, comma mean. You can choose the median also. B2a is 2a and 2b is Mplus lingo for the between level for time, whereas 2b is the between level for subject. So anyway, this is alpha sub t, the estimated alpha sub t quantities over time. And you see a trend, right? It's a trend that you can interpret. It has to do with smoking urge. So there's something that seems to go down and then level off, which looks kind of substantively interesting. And we may build on that insight. So now the runtime is 1 minute and 10 seconds, not bad at all. Much thanks to only random intercept, nothing else random. Now we can take this impression of trend, which is totally non-parametric. We have not imposed any shape on this trend. This is what we observe in the data. In data as much as the model filters it, but we have not specified a functional form for it. Now we can specify a functional form like a linear or a quadratic, both in a cross-classified analysis and in a two-level analysis. And when we do it in a two-level analysis, a few minutes from now, we're going to come back to growth modeling of the wide single-level form and recognize that again in this shape. So this is kind of fun. So don't get lost. So first of all, we impose linear quadratic trend in the cross-classified case. So just adding to the cross-classified analysis that we talked about. So we still have cluster equals subject and time QD, and we still have analysis type cross-classified random. Now we're going to define two time variables, time and time 2. This is the linear part, this is the quadratic part. Because the time QD variable is on such a high scale, I'm dividing it down by 100 to just make it more manageable. But that's not essential. But those are variables we're going to use in the model, and therefore we have to declare which level they vary across. And we're going to say that time 1, time and time 2 are going to vary on the time level, time QD, the between time level, which is down here, right? Between time, that's where those variables appear. Not for the between subject, but between time. And the way you say that in Mplus, you put the level in parentheses and then the variables. And then you can have another parenthesis for variables that vary across people instead, rather than across time. So here we specify a functional form for the urge by regressing it on those two time variables. And here's what it looks like. Here's when you make it linear, that is, you only use the time variable, not the time 2 variable. Here's when you use time and time 2. And you see that you have a tighter fit to this curve for the quadratic than for the linear, suggesting that you should go with the quadratic in this case. We haven't done growth modeling here. We have done we're looking at the shape of the urge development over time. There's not a random regression across over time. So now we want to get back to how we model trends in two-level modeling. Recall how growth modeling can be transformed from wide to long. Use this picture again. It's a single level wide format analysis, 5 columns of data. But we can think about it as what's above the broken line here is across time within level variation, and what's below the broken line is across individual between level variation. And therefore it is conceptually easy then to move to the two-level long format, where again we regress y on time, like we talked about before the break, with a random intercept and a random slope. And that's all happening on within. Like we said, we could do a regression for each individual and get each individual's I and S values. But here's an analysis of everybody together, a more efficient way of dealing with the data. And then on the between level, we have variation across people and a subject or family specific variable influencing I and S. The two-level counterpart to that looks like this. So the headings are really important here. We're now jumping to the two-level time series setting, adding a trend for urge, and we're going to think of that as a growth analysis with a time-varying covariate. So the trend is captured here. Urge is regressed on the time variable with a random slope and a random intercept. But we also have negative affect influencing urge. So negative affect is then a time-varying covariate. You know, we had a picture with time-varying covariates early on, before the break. And here then we have a random intercept, a random phi, a random log variance, a random regression of urge on NA at the same time point, and now a random slope. That is, the trend over time is different for different individuals because S varies across individuals. So that's time series trend analysis formulation. Now the interpretation of S here is not the usual one of growth modeling for the very reason that we put the autoregression on the variable, not on its residual. But again, soon enough, we're going to be able to put it on the residual, and it would be a perfect correspondence. And again, Hammacher's paper comes into play to discuss the differences. But this is what it looks like on the within level, and then all of these filled circles become open circles, continuous latent variables on between. So I did this for the smoking data, and now we're back to two-level analysis, which you see by cluster being subject alone and analysis type being two-level. And we have the between-level variables, female age, and now we add a distal outcome, quit. Quit smoke, successfully quit or didn't successfully quit. It's a binary variable, so we declare it as categorical, and it's a between-level variable. It's a variable that varies across subjects. And then we put time and negative affect on the within level. Time, because now we're going to do growth modeling, essentially trend analysis, growth modeling, same thing. And it's a within level variable. And we're going to lag both urge and negative affect. It's going to stick to the time interval 0.08, even though it may not be optimal. And we're going to define a time variable, which is essentially the time since quitting, but scaled down and centered here. This is the observed mean for that variable that I subtracted, just for simplicity. And again, I do group mean centering of negative affect and the standard base 3 lines here. And in the model command with a colon, you have the within specification, the same thing here, the random phi, random SYX, random log V, plus now the random slope, urge on time. So here we know now we know this is growth modeling that we're doing. Because on within we have a random slope. We're saying that people change over time, they grow or decline over time at different speeds, varying across subjects. And then we have more variables here in the on statement. 1, 2, 3, 4, 5 random things, S added to it, regressed on the background variables for the person. And we add this what I call a distal outcome, to use preventive intervention terms, quit on these random effects plus the 2 observed background variables. And this is now a regression for a binary dependent variable, and in base, the only thing we have available is probit. Base is totally probit. Maybe one day it could be loaded if we wanted to, but probit is a very general approach that allows underlying multivariate normality to allow with statements even among categorical variables very easily without adding numerical integration like maximum likelihood suffers from. And we have the usual take 1, take 8 and FS comparison, and we ask for access to the factor score values to plot. The runtime is almost 5 minutes, and here's what it looks like. 2-level regression analysis. I call it regression analysis because it's regression of smoking urge on negative affect, adding a trend for urge, or it can be characterized as a growth analysis with a time-varying covariate. What's new in this picture is that we've added the random slope for the development over time, and we've added the distal outcome quit. We looked at these relationships before. Now we can look at these. So I have the interpretations of these pluses and minuses here written down, so you don't have to scribble them, but can think about it instead. So this is saying that the higher the urge level is, the lower the probability of quitting. The higher the level of smoking urge is, the lower the probability of quitting. That makes sense, right? Now, what we didn't know was, or couldn't have guessed, is that the higher the autocorrelation, the higher the quit probability is. The higher the autocorrelation, the higher the quit probability is. That takes a good substantive researcher to tease out, assuming that the model is correctly specified. And that's assuming a lot now. This has to do with the variation in smoking urge, and we're saying the higher the variation, the lower the quit probability. So if you vary up and down in the smoking urge, like subject 227 did, that person has a lower probability of quitting smoking. No significant effect for the random slope of y on x, that is smoking urge on negative affect, and however a negative effect of s on quit, meaning that the higher the slope, the higher the smoking urge slope is, it goes down, but the higher it is, the lower the quit probability. That is, if the smoking urge doesn't go down enough, then you're not going to quit. The higher it is, albeit negative, the lower the quit probability. So that's what it says here. So that's just an example of what kind of stories you can tease out of the data. And again, it's two-level analysis, adding a trend and a time-varying covariate, which you don't see on between because it's a within variable. That is the negative affect. Now that relates to a topic that's become quite popular, particularly with the help of Penn State analysts coming up with time-varying effect modeling using splines. What it means is that we allow parameters to change over time, not only change over subject. And we've already gotten into looking at variation across time, right? And here we're going to take a look at the regression slope and ask the question as an example: does the influence of negative affect on smoking urge decline over time? That could be of substantive interest, right? If you uncouple this relationship between wanting to smoke when you feel irritated, if you make that relationship weaker, or if that relationship weakens over time for reasons of some physiological reason that I don't know about, then you would want to know that, because that is perhaps the key to successful smoking, quitting smoking. So does that SYX decline over time is the question. So then we do a cross-classified analysis. That's what we use for anything that changes over time here in coefficients, adding a trend for urge and the negative regression slope. I can have a trend also. So on the between subject level, we simplify the model now. So we only have the intercept, SYX, and the trend as random, influencing the quit variable. And between time, which we have access to in the cross-classified analysis, we can let SYX vary as a function of time. So we can estimate this coefficient. If this is negative, it means that the SYX value goes down across time. So cross-classified analysis, cluster subject time QD, type goes cross-random, you don't have to write out cross-classified. Between subject is female age quit. Between time is time t. Time t is defined here. It's equal to time w, the within time, which is the time we use for the growth modeling. And how do we do it? We have within, we have between subject, we have between time. Here is the random slope that defines a random growth factor S. On between time, we say that the random slope of y on x, smoking urge on negative affect, is regressed on time t. So we want to see if that is a significant drop over time. And we don't need to have S, the random growth slope, vary across time as well. It's sort of cake upon cake, to use a Swedish expression. We already have S, we already have a development over time. It can be estimated, but it's hard to deal with. Anyway, 34 minutes, but not too bad. So here's what it looks like. The output says that the regression coefficient of the random SYX on time t is negative and significant. So there is a lowering of SYX over time. It's just that we have to understand what's happening here. So we could conclude that the effect of negative affect on smoking urge is reduced over time. Once again, you have to be reminded of the fact that that coefficient, this is the estimated alpha t. So it's in formulas, it's alpha hat sub t that we have on the y-axis. So it has mean 0 here, positive values, negative values. It does not imply, as I sometimes slip into thinking, it does not imply that the regression coefficient of urge on time becomes negative. SYX is the regression of urge on negative affect. It doesn't mean that that becomes negative. It makes more substantive sense that it's positive. High irritability gives high smoking urge. It just means that it changes in values across time. It reduces in value across time. So SYX percent 2a, like it says here, is between time factor score part of the SYX slope. Its mean is 0. The full SYX slope, however, the full SYX slope mean is expressed as on the next slide. So you have to do it this way. Let me first show you the result and then show you what we did. So if you look at males here, time t minus 1 is early on in the quit attempt. Then the regression coefficients for smoking urge on negative affect is 0.63. Time 0 is in the middle of the time. It goes down to 0.47. Time 1 is very late, and it goes down to 0.32. So you have this decrease in the smoking, in the regression coefficient over time. And the way I calculated that is the estimated mean of SYX given the time t, given female, given the gender variable, which is 0 in this case for male, and given age, is equal to the intercept here, and the negative regression coefficient on time t, that's the one that was significant, from the between time level, plus the between subject level part, because it's SYX is also influenced by female and by age, although the coefficient is 0. So from this expression and these values you get from the output, I can compute these values that come up here. So we're concluding that irritability and negative affect has less of an influence the further into the quitting smoking process progresses, goes along. Are you ready for the last topic? The optimal outcome is that we do that in 35 minutes and then have questions and answers, and then the party begins out there. So we're going to get into latent variable time series analysis, which Ellen touched on a little bit, and Ellen will come back to that topic with an application that's interesting in the last block or part 8, late tomorrow afternoon, which is going to be a mixture, a medley of me talking, Ellen talking, Tiamer talking, Ellen and Tiamer having these leftovers probably, Tiamer too, and so that's a leftover time, plus some novelties as well. That are not exactly leftovers. So now we're going to talk about time series analysis with latent variables, and we're going to talk about formulating latent variables on the within level In particular, we're going to talk about factors. So far, we focused on latent variables on the between level, you know, the random effects, the open circles. Although on within, we actually have used the latent variable within level decomposition of the outcome. We have centered by YBI. That is, the latent within part of the outcome Y is obtained as the observed Y minus the between component, the subject-specific component. I think Ellen called that mu sub I. And she called this Y to the power of, in parentheses, superscript, Y superscript in parentheses W. But now we're going to introduce what I would think of as real within level factors. We're going to talk about factors defined by single indicators with measurement error, which you might think is not possible, but it is. In time series analysis, a lot more things are possible. We're going to briefly touch on ARMA modeling, and then we're going to focus on factors defined by multiple indicators, the usual kind of factors, still on the within level. And we're going to do that in a two-level and cross-classified analysis setting. This has to do with continuous latent variables. And when I say factors or random effects, I think about continuous latent variables. But we also dabbled in the categorical latent variable area, that is latent class variables, mixture modeling. And that's going to be in version 8.x, where x, as usual, is an unknown. Although the article is already published, so why should we even model it? I mean, program it. Well, it's interesting model opportunities arise if we get that going. It's quite complicated, and TMR has done some neat groundwork, but much more is needed. What the hope is then to be able to do transition modeling, which is also called hidden Markov or regime switching or time series latent transition analysis, where the latent variable is a categorical latent class variable changing over time. And you could then, in principle, also do growth mixture modeling of time series data. So that could be quite exciting, but we're not there yet. Now, single indicator measurement error models could be described like this. And it's interesting that this is even possible. And it is possible because if you look at it, you have the factor, the latent variable here, and the observed indicator of it here. You have two residuals, one up here, one down here. This is sometimes called the dynamic error. I think Ellen called it Z or zeta. This, however, is the measurement error. And the saving grace, that is why you can identify this model, is because they play different roles. And Ellen started talking about that. This dynamic error carries over to the next time point. This dynamic error influences and is part of f sub t, which influences f sub t plus 1 in this time series. So this error carries on into these latent variables forward. This error, however, does not carry on. It's an independent error at that time point, has nothing to do with the error at the next time point. So they play different roles, and therefore it's possible to identify. So that's often called white noise, uncorrelated error like that. And the model is identified thanks to this time series feature, unlike regular factor analysis. And it's because of the time series autoregressive feature, which has occurred also in the short time series literature, the panel data modeling. Already in 1977, this was written about that you could identify measurement error in a panel data, in a longitudinal data set that is not intensive longitudinal data. That's a very nice article by Noemi Schurman in 2015 in Frontiers of Psychology, which I really recommend because it's n equals 1. So you could do this modeling for n equals 1 or for n greater than 1. And this is really an inspiring paper for learning about how to get the most out of n equals 1 data. The input for the measurement error model is like this. Cluster is subject, so we're talking two-level analysis. And we have within and between. Between is between subject. And to match the model here, we have f measured by y. So the standard f measured by y. At 1, I say, that's superfluous. That's default that the first indicator is fixed at 1, first and only in this case. And then we say that the factor f also exists in its lagged form with lag 1. And then we put the autoregression on the latent variable, on the factor level, s here. Oops. Wants to go the other way. That s is this. So if you want to scribble, s sits here. This is s. And then on between, you let the random intercept be correlated with the random slope. Random intercept sits here, correlated with the random slope. That's easy, right? Now there's a related model that Schumann paper talk about, and it's more related to the time series literature, a so-called autoregressive moving average model, autoregressive lag 1 and moving average lag 1. And it can be drawn like this. Yt regressed on yt minus 1. And what's happening here is yt is influenced by yt minus 1, but also by the error for yt minus 1 at the previous time point, plus the error at this time point, which then influences y at the next time point. And you can have the intercept and that slope random as well. I don't know if that can be random. Anyway, you would write it like this. And E, and this is the E, is measured by y at 1. But you have no measurement error here. So you fix that measurement error variance to something small. Bayesian analysis does not like fixing things at 0. Then you get bad mixing. So that's a drawback relative to maximum likelihood. So that's why you fix it to a small value. And then you put the regression of y on E at 1, E ampersand 1, which is this one. So the last line here, you can connect that to this. And then, but that's not random. I don't know what would happen if that's random. Anyway, this model doesn't work as smoothly in Mplus as this measurement error model. And the reason I say that is because they're related. On slide 81, it says that Granger and Morris, 1976, and Sherman show that for n equal to 1 time series analysis, ARMA 1,1 is an alternative representation of the data used in the measurement error model. And they show formless translation of these parameters. These two parameter sets. A measurement error model can always be done in an ARMA setting, but the reverse is not true. So the ARMA parameter space is a little wider than the measurement error space. But why would one want to do the ARMA model version of measurement error modeling when the measurement error modeling works so much smoother in Mplus? I don't know. So anyway, this is a statement. Measurement error formulation converges more smoothly than ARMA. This is a model, the measurement error model is a model that Thiamer really likes. He calls it the MEAR model, measurement error autoregressive. So he'll talk about that tomorrow. The n equals 1 versions of these models for ARMA now require a very large t, but preliminary simulation indicate that the multi-level versions have good performance at much lower t values, suitable for daily diary designs. Thiamer likes this because the measurement error model avoids the autoregressive model assumption or specification that you have exponential decay in the autocorrelation. The autocorrelation goes down very quickly. The measurement error model allows a slower, more realistic decay. He'll talk about that. Now the measurement error model is very nice because you only have to have one indicator and still pick up measurement error. You know, what's not to love about that? But it seems to me, at least, preliminary observation is that it's more difficult to add random residual variance to the factor in the measurement error model. I haven't done thorough simulations to know that for sure. And actually an interesting research question is a paper, how does performance compare for this single indicator to having multiple indicators? That is, if you take the average of the positive affect items and work with the measurement error model with one indicator, how does that relate to working with all 10 indicators of a factor? Which is best in various regards? And is random error variance easier when you have multiple indicators for the factor? In the user's guide 9.34, we go through a couple of factor analysis model specifications. You have within and between here. And again, we draw it for 2 time points. You have random intercepts for each of the indicators, a random autoregression, and a random residual variance. The random intercepts become latent factor indicators on between. You're used to that if you've done 2-level factor analysis. So these open circles are the random intercepts here. You can put a factor behind them, a factor on the between level that explains the correlation between them, or you can let them be freely correlated or whatever you want to do. And then you have S, that's S, and log V, that's log V, also random on between. This figure has been called the DAFS model, direct autoregressive factor score model on within. An alternative is the WNFS model, white noise factor score model, which has FT-1 influencing the indicators directly and not going through FT. And to specify that, you say Y1 through Y4 regressed on F(1) instead of F on F(1). So you don't have it there, you have it directly like that. But a combination of the models, the 2 models, DAFS and WNFS, is also possible, although it may need a large number of time points. This goes back to n=1 articles in Journal of American Statistical Association and in Psychometrica. In the n=1 case, they describe these models. But we do it in the n greater than 1 case by these random effects. Cross-classified factor analysis is possible too. And then you let these random effects vary not only across subjects, but have these random intercept vary also across time. So you can have a subject factor and a time factor. And not much has been applied in that area, so it's a wide open area for application. Which leads us to this slide, and I know it's late in the day, but you can do it. It's an exciting story if you penetrate it. Because all of these random effects, now when it's random effects for, if you go back to this, we talk about random effects for the intercepts of the factor indicators. The intercept of a factor indicator is a measurement parameter, right? Measurement parameter is the intercept and the slopes, right? If you think factor analysis. I mean, there's certain things that are still true out there, even though we've gone wild here now. So when measurement parameters like random intercepts vary across people, it seems like we don't have measurement invariance anymore. So it relates to measurement invariance concept. And that, to see that, you can get back to 2-level factor analysis, which has been written about by many people, including MacDonald and others. And I wrote a 1994 paper. So you can decompose Y in terms of a between-level factor model, loading times factor plus residual, and a within component, loading times factor on within plus residual. So that's a 2-level factor analysis model, and very often you find that you have very many more factors on the within level for the person in that case than on the between level, which is sort of for the school. So this could be math and reading ability, and this could be school excellence. So 2 factors versus 1. And certainly you do not always have the same loadings even when you have the same number of factors. Now if you look at that long enough, you can see that that can be written as a 2-level model with a random intercept. This is nu, NU, the random intercept. It's a random intercept because you have subscript I there. If you write that as nu plus lambda b plus epsilon b, insert that expression here, you get back to up here. It's just that this is written in a, at least statistically, provocative way. showing that you don't have measurement invariance across people, because it varies here. Random intercept model is measurement non-invariance across subjects with respect to the intercepts. And that was written about in the journal Structural Equation Modeling by a Dutch researcher, Jaak. There are a lot of Dutch people involved in this business, which is nice. So 2 articles there. And we have dabbled in that area too. This is an article that's forthcoming in SMNR, Sociological Methods and Research. It's not out yet, I don't think. It's a special issue on measurement non-invariance, where we talk about random effects modeling for intercepts and loadings. Now, item response theory makes a simplifying assumption, which Ellen is going to give an example of tomorrow afternoon when she continues her latent variable factor analysis modeling. They make the assumption that the within and between loadings are the same, and the measurement error, or the residual on the between level, is 0. So lambda b equals lambda w, and this vanishes. This is gone. Then the level 1 model, using this expression, can be written like this. Because if you don't have b here, and if this is equal to that, and you put it in, then this lambda multiplies an f, a factor, which is the sum of the two. That lambda multiplies the between part and the within part by the same value. So that's the equality. The advantage of looking at the modeling this way, which Ellen will show an example of, is that you have no non-invariance, which is the same thing as saying you have invariance. And you have the factor you have a single factor dimension f, instead of having 2 different kinds of dimensions, fw and fb. So just to see, get a perspective here, getting a bird's eye view of the area, connecting what we know about measurement invariance and non-invariance, and this modeling that we're talking about now, 2-level factor analysis and dynamic 2-level factor analysis. So just a summary of this, what Mplus version 8 offers is 2-level analysis with random intercept that can vary across subjects. I'm talking about factor analysis now. Random loadings that can vary across subjects using a bar statement for a set of slopes, f by y1 to y10. So the slopes are the loadings here. This existed already in version 7, but I have a feeling it's underutilized again. So much happened in version 7 5 years ago that that was perhaps too much. We didn't have time to write enough application papers on it. But there's an article, a chapter here, and you have the reference at the end. And Jean-Paul Fox, is that another Dutch? Another Dutch?
Yes.
Okay. A very good researcher too. It's a book on Bayesian analysis of IRT where he talks about these random measurement parameters. Cross-classified analysis, random intercept can vary across vary across subjects and time. Random loadings can vary across subjects only, not time yet. Version 7.4 had cross-classified analysis with random intercept and loadings, but it did not have autocorrelation, which is needed for intensive longitudinal data. So, and that cross-classified analysis needed many time points, but when you have many time points, they're often closely spaced in time, and therefore you need the autocorrelation. So we almost had it, but not quite, which was pointed out to us by Jean-Paul Laurenceau, which sits over there. So he has had a hand in this. For an example of random loadings varying across subjects, see the user's guide 9.40, the last example, last part. All right. Subject-specific reliability comes into play also, not only subject-specific measurements. And intercept and loadings varying, factor variance and residual variance varying across subjects and time implies the reliability of test scores vary across subject and time. This is an article that touched on that. We're not going to focus on that slide. We're going to take it easy instead and talk about a final example which moves us beyond the smoking data but keeps us in the realm of negative affect. The irritability matters, and we're going to do a factor analysis of the negative affect items, and there are 10 of them. We're going to call it Item factor analysis or item response modeling, item response theory modeling, one and the same thing to me. So we're going to assume that there's one factor here. There probably are more than one factor behind negative affect, but although we don't quite have the right tools to assess that quite yet. The data come from a Notre Dame study by Cindy Bergerman, where you have 270 people and 56 time points, daily measures on consecutive days. And that was described in an article in Psychological Methods by Wang and somebody called Hammacher and Bergerman in 2012. So that article was a real inspiration to me because it really stressed what the important parameters are that we should let vary across subjects. The primary three. Intercept, phi, and variance. Those are the three important ones. That trio, they had that done there. And for these data. So the predictors and distal outcomes of negative affect development over the 56 days was their concern. So they had this mediation situation that I showed. You know, the female and age influencing the random effects influencing the distal quit outcome. It's mediation on the between level. And for those of you who were here yesterday, it has a binary outcome and multiple mediators that are latent. That calls for counterfactually defined effects, which can be done by the techniques we learned yesterday, at least through model constraint, to get the right indirect and direct effect for that quit probability on the between level of a time series analysis that's multi-level. Anyway, back to this story. 10 negative affect items. Each item is on a 5-category scale. And the items have to do with being afraid, ashamed, guilty, hostile, scared, upset, irritable, jittery, nervous, distressed. The average score was used in the article. Now, you can certainly do a wide format analysis for 56 time points, single wide format analysis, but so T is 56, but you have 10 variables for each time point, so that would be 560 variables. That's a little wide. Big covariance matrices, heavy computations. Instead, we're going to take a 2-level analysis, or perhaps a cross-classified analysis. We'll see on the next slide. Just to remind you, the question format is today I felt afraid, today I felt irritable, not at all to 5, which is 1, to 5, which is extremely. We're going to take a one-factor DAPS model approach to this. Here is a distribution of the variable in the Bergerman data. This is the average score. Looks like this, strongly skewed. Very high piling up, strong floor effect, 55% floor value 1, which is saying, today I felt not at all any of those 10 items. So these are people who didn't have any negative affect at all. Here's a typical item distribution. This is the average. Here's for the item, you know, with 1, 2, 3, 4, 5 scale scores. 66% at the lowest value. And this is for the seemingly common item of irritability. Who isn't irritated at some point? You know, but still, 66% say they were not at all. So what do you do with data like this? Well, maybe this is continuous censored, but it's not a great candidate for censored, mostly because this distribution here in the tail doesn't come down towards 0 before to the right of the pile at the floor value. So maybe a better approach is to not work with the average, but go down to the item level and model this instead. And as I said yesterday morning, if you take a categorical variable approach, treat this as an ordinal variable, there is no violation of assumptions by having a pile, very high pile, very strong floor effect here. That doesn't violate any assumptions of the ordinal logistic regression or probability regression approach. So the ordered categorical item modeling, which in statistics is called proportional odds modeling, and in IRT is called graded response modeling. The outcome y looks like this, like we just saw, but the way it's modeled is through a continuous latent response variable y star, which has response categories demarked by thresholds here, tau 1, tau being the threshold, tau 1, tau 2, tau 3, tau 4. And the fact that these thresholds are towards the right of the tail means that you have a very low probability of being down here, corresponding to the high pile here, and very small probability in between the thresholds up here, corresponding to small piles of y up there. So I'm saying that despite you have a non-normal y, truly non-normal, we can have normality of the y star behind each item, latent response variable, and we can have normality of any factors in the model, and we can have normality of the between level random effects. Actually, these normality assumptions for the random effects is a topic that's been under study by Morten Schultzberg and Ellen Hammacher, and Morten is going to describe that in part 7 tomorrow after lunch, what he's found so far. Here's the input, and we do cross-classified factor analysis, more general than the two-level factor analysis. One factor, 10 ordinal negative affect items. So we declare the 10 items as categorical. And we have two cluster variables, subjects and day, for these diary data. And we have t-interval day 1 here, an easy choice of the binning, cross-classified random, the base stuff, and then thinning because we want to avoid high order correlation. Perhaps it should be even a higher thinning. Thinning equals 100, which would slow it down further. But in any case, this is a harder thing to estimate, and therefore you may need to thin, that is skip, only use every 10th draw, or every 10th iteration in the Bayesian iterations to describe the posterior distribution of the parameter estimates. So we're going to use the IRT style of loading equality, setting the factor metric on the subject level. And what do I mean by that? Well, cross-classified factor analysis, within, between subject, between day. So within, you say negative affect underscore within is measured by, that continuous latent variable is measured by these 10 items that have been declared categorical. So this says then that those items have a probit regression on this continuous latent factor, right? They're indicators of it, which means they have probit regression onto the factor. The factor is the so-called x variable here then. And we hold all of those factor loadings free for reasons that will become clear. And we define the factor with lag 1. And after that, space, and then we give labels, parameter labels 1 through 10, corresponding to the 10 free loadings here. And then we do autoregression of that within factor onto itself, not random at this point, but fixed. And between subjects, we measured the negative affect on the subject level by the same items, that is the random intercepts, all free, and we set them equal to the one on the within level, so that lambda between equals lambda within issue. Now we have 10 free factor loadings, so somewhere we have, well, let me just take it further. Then we have between day variation, so we have negative affect for the time, measured by those same random intercepts, but now varying across time and still equal across levels. So this is sort of a cross-level version of the IRT style equality loading. We have 10 free loadings, I began to say, and somewhere we need to set the metric. That is, you can fix the factor variance to 1, and I chose to do it on the subject level here. But there could be a cottage industry of papers trying to decide where you should set the factor metric and how you should set it, which probably will happen. Runtime for this is 54 minutes on my old computer. Dichotomous 34 minutes, continuous 16. You wouldn't want to do continuous. You could imagine dichotomizing it because they're so heavily skewed each item. But using all the data as is, 54 minutes. So it's a little slower. Here are the results. 1 factor for 10 ordinal items. We have to remind ourselves what cross-classified analysis does. So I repeated this equation that we saw before, but now the factor is the dependent variable. So we have the between subject variation, the between time variation, and the within subject variation. And the between subject is standardized to 1, and the between time is very small. Within time is very high, much higher than between time, but still a little bit lower than between subject. This is probably a typical rank order between them. But even though the variation across time, that is the alpha t variation, is fairly small, exciting things happen. You can plot this estimated factor scores for alpha sub t, so alpha hat sub t, across time. So you have the days here up to 56, and the factor score on the y-axis, NA time. And you see that the average is 0, but you see that there's a downward trend of that. So it says that the factor, the total factor, then has a downward trend thanks to alpha t. And we were at the International Meeting of Psychometric Society in Zurich, Switzerland in July, and got help with some interpretation of this how this looks. It's well known from the literature that psychological measures, mental health measures, have a tendency to have a J-shaped form, that is high values right away and then dipping down low. It's sort of a reporting phenomenon, which we see here. Then things tend to stabilize here, but then much less reporting of negative affect towards the higher days. Perhaps due to fatigue of the respondents. I don't know. I mean, I'm just suggesting a story. And so perhaps this underestimates it late in the game, and perhaps this overestimates it late in the game. Perhaps you should focus on negative affect values in this time period from day 10 to day 40. That's the kind of reasoning that you get out of a plot like that. So it tells you a little bit about measurement and how measurements should be designed and when they should measure and how long they should measure. You also get the posterior distributions of these factors on within and on between and between time. So within, it's not too far from normal, but it's a little bit skewed, and that's a little bit skewed, but not too bad. And that's not too far from normal either. But again, the factor distribution is going to be discussed by Morten Schultzberg tomorrow after lunch, so I'm not going to get into it. And with that, at 4:30, we have the encouragement that submit your papers to be posted here. You are welcome to dig into this and tell us about your success stories. Thank you. All right, so we have 15 minutes left for questions.
So I have a question regarding slide 69, where you described in the last line that the higher trend slope gives lower quit probability. Mm-hmm. By higher, you said even though it was negative. Do you mean the absolute value, or do you mean just higher regardless of sign? So just approaching.
So if the average is like this, I'm thinking that when it increases like this, that is getting towards flat. That is the urge level doesn't go down quickly enough. The person has a low probability of quitting. They have too strong of an urge. It's a little tricky when you talk about negative slopes and effects, but it means that this person is higher than average. So therefore closer to a flat line of urge. Urge doesn't go down. Quit probability is low.
Okay. And I have a second question about, sorry. Oh, on slide 74,
Slide 74.
when you talk about the effect of the negative affect on smoking urge is reduced over time, could this be related to there being more variance around negative affect to begin with, and therefore it's kind of a diluted contributor?
Could you say the last part of your question again?
Could this be related to there being more variance around negative affect in general, such that it's kind of a diluted contributor over time? Because I noticed that back on slide,
Oh, because we saw that in the Bergman data, you mean?
right,
In the last data set. Yeah.
right,
It's not the same data set, so I don't know. The negative affect distribution is actually quite different in the two data sets. It's very skewed in the Bergman data that we did the factor analysis on, but for the smoking sample, it's quite normal.
Okay.
These smokers are high-wired. I mean, they're irritable. bunch.
And then you keep
Thank you.
asking them if they have the urge to smoke.
I'm sorry, what?
And then you keep asking them over and over if they have the urge to
Yeah,
smoke.
right. It's really irritating. So I don't know, but that's an interesting angle. Does it have to do, the lower slope doesn't have to do with change in variance over time. That's a good point.
I have a question.
Yes.
So I work with a lot of biomechanists who tend to conduct studies on a small number of people, but they'll measure things in time series. So they'll measure EMG forces on a AMG on a muscle while somebody's doing a task, or they'll measure forces on a joint while they're doing a task. And what they tend to do with the data is collapse it in much the same way that you showed the animation for the Bayesian time series onto a distribution, and then pull out a particular parameter from the distribution to analyze. And I'm wondering if you've seen any biomechanists trying to use some of these techniques to look at these data more dynamically.
By the way, you reminded me that I didn't give proper credit for that movie. That's Morten Schultzberg's doing.
Yeah.
So do we have any biomechanical person in the audience?
I'm just really excited about this because I can see lots of applications for these data that they're collecting to look at it in a different way, and we might see different things.
Right. So part of your question is how can we do good analysis with few people but many, many time points? I think that again falls in the lap of part 7 tomorrow afternoon.
Okay.
And it's related to work maybe also by people like Steve Boker and Simin Chow, which they have data like.
Do you want to talk into that microphone?
Oh, yeah. Getting there. So people like Simin Chow and Steve Boker, they use data like the movement of people's heads during conversations and this kind of stuff. So, and they definitely look at the dynamics. So what you are saying is like when you collapse it, you get a summary of the distribution, but you lose all the information about the dynamics. And they specifically use continuous time models to model the dynamics of those kind of data.
So I might come and ask you about those names later.
Sure.
Okay, thanks.
On slide 68, I just had
Slide 68?
Yeah, I had a quick question about the code. So for the first line under between with urge, no, keep going down. For the first code of line under between, yeah. So for urge, SYX, S, so on, you mentioned that those were random effects. Can you clarify the random effect that is urge in that line of code, please?
Yeah, so when I refer to urge here, that's the random intercept, or actually it's which turns out to be a random mean.
Okay.
So that's the mu sub I in Ellen's presentation.
Okay, thank you.
Yeah.
Yeah.
On slide 60, with the cross-classified, so the time QD as one of the cluster IDs, is that the bin number essentially that's created with the T interval in terms of identifying the cluster membership for that cross-classified?
Yeah, these two variables are the same, but here, the binning here creates a new time variable that's used in the actual analysis.
But when you're putting I mean, in terms of the cluster ID, right? if everyone's time, if it's a continuous time, then observations will go into the same bin, but the actual, recorded time QD value is going to be different for every single observation, potentially. But you're binning them. So is it the bins that form the cluster ID for time?
Timur, why don't you come up and take that question at the microphone there?
Yeah, that's right.
Why didn't I think of that?
This is already the integers. Yeah.
Could you repeat Catherine's conclusion?
So the question is if this is a cluster variable, so you can't really be the continuous time variable, which is takes all kinds of values.
Right.
So when we are using this. So this is about how the t-interval command works in cross-classified models, and that's how it works. We first make it an integer in whichever, using the algorithm, and it's a slightly different algorithm for cross-classified than it's for two-level because the time scale is aligned. But we first make it into an integer, and then we do use it as the integer as the cluster command, basically.
So are you saying that this time QD variable in the cluster setting is the one that's created by t-interval?
Right. Mm-hmm.
And it's not the original time QD sitting that up there?
It's correct, yeah. We can't accept, Mplus wouldn't actually take a non-integer cluster variable.
So this variable could be like 1.32 or 0.32 that we saw, and we turn it into, say, 1 by this statement, and that's the value for time QD that's used for the cluster variable. Was that what you asked?
Yeah.
Good. All right. Thank you, Timur.
I had a question about slide 57.
Slide 57. I'm learning a lot here.
So I was wondering if this comparison between autocorrelation with the regular and the residual is something you can do on the current version of Mplus, or is that upcoming?
This is upcoming. Version 8.1 is upcoming. So this line you cannot do in 8.0. You can only do this. You can only do that, not that.
Okay, thank you.
Yep.
Actually, I want to say something about it.
Yeah.
So, we do have, you can do it. The language isn't available. The model is available, with this mirror approximation. So I'll talk about this tomorrow. But, technically you can do it.
Technically you can do it, but it doesn't work as well as it will in 8.1.
So the algorithm that comes in version 8.1 is very efficient. So we were just talking with JP about this, and he had to take 50,000 iterations, I think, to get it to converge for the example that he worked with. But now with this simulation study that we're running in the developmental version, this algorithm converges in 200 iterations. It's like one bam bam and it's done. So it's worth it to actually get this algorithm actually implemented fully and available, because it's so much more efficient than the current implementation, which basically goes through the mirror model.
Yeah.
So
How fast did you say that it converged?
bam bam.
Hi, JP.
Thank you, Bank.
Are you going to ask another question that sends us back 5 years?
Well, thank you for this presentation. I did have a question about this slide and the previous slide, actually. So, I've been thinking about this issue a lot. And the next slide kind of implies that one of the ways that you should decide is based on fit, right? And I'm thinking about this more, now if you go back to the previous slide, I'm thinking from more a substantive perspective. It even seems that I could envision a situation where you actually can estimate both auto-regression
I see
and
Timur approaching the microphone here.
correlation.
So we actually have like about 10 slides on this tomorrow, and we call this the joint effect model that has that has both. Well, actually, sorry, I may be interrupted.
Oh, no, you probably are figuring it out already, but I'm just.
So
thinking
you're
about
saying having both this and this. I think Timur is going to talk about effects of negative affect.
No, is that what you were talking about?
Yeah, because substantively, I can envision that even if you take into account earlier urges predicting later urges, that, for example, there could be, like if you have a cold on a particular day, maybe that affects your urge the next day, separate from the urge itself, And so I'm just wondering if you had any thoughts on that. I'm not expecting you to build this in, anytime soon. If it's even possible, you probably need more data to be able to even identify this model, more predictors. But substantively, I guess the point is,
You can imagine both.
I can imagine both, even though on the next slide you're suggesting that really kind of you decide based on fit, whereas I'm thinking perhaps the question can guide which one really is the one you should use.
Sure.
Just for me, when I was thinking about this, was basically whether to put the regression on the predictor within the autoregressive equation or outside of the autoregressive equation, and we.
So it has to do with this regression, right, that you were thinking about?
Whether that, and now we know that you can actually have you can have the effect of the covariate in both in the autoregressive equation and outside of the autoregressive equation. So that's what I was gonna show tomorrow, some simulations and explain that model. But that might very well be the case. I have not run any models like that, but
Once
seems quite
again,
reasonable
you've
that
given
you'll
us
be,
something to think about.
Yeah, it probably is identified. So.
Every 5 years he comes around and... All right. Yeah, okay, great, thanks.
This might be one of your easier questions of the afternoon. On slide 87, when you talk about 56 times 10 variables, is the limit for Mplus still 500 variables per model? Or is that limit changed?
In a single wide format analysis?
Yeah.
Is the limit 500 variables?
I think I changed it.
I think we changed, I think we increased it.
What is it now, out of curiosity?
I think it's probably 1,000. I
Yeah.
have no idea. So
No, but that sounds familiar to me. This is where we have to ask Trine and Wen.
That's what he said in Zurich.
Oh yeah.
1,000.
What did you say?
He said that when we were in Zurich.
Oh, good, you have good memory. All right, next question. Here we have people, oh, okay. Go ahead, person who has the microphone.
I had the mic, so I just thought I'd start.
There you are.
So something that we do a lot, we do daily diary study, and instead of getting the variance for each individual, we'll get the mean squared successive deviation.
Right.
Which some people argue is more more so what you want to get at for time series data. Have you guys thought about that within your framework?
I have noticed that measure, and I wondered myself. So it sounds almost like it has to do with amplitude. Ellen has some thoughts on that.
Yeah, actually that's discussed in the paper with Wang as the first author, so Wang, Hamaker, and Bergeman. And we compare the mean successive difference, squared successive difference, as you'd say, with the multi-level AR1 model. So, and it's, I guess you could argue for both, but in the paper, what we argue is that if you look at the mean squared successive difference, this combines both autoregression and individual differences in autoregression and individual differences in variance. So it depends on how you want to look at it. Sometimes I think it's a good idea, but if you think about the mean squared successive difference as a model, like it's the variance of the square of the difference, it's like an AR1 model where you fix the AR parameter to 1. So it's like a random walk. And that's definitely not what most variables behave like. So it's not so much, I would say it's not a model, it's more a descriptive measure. Whereas an AR1 model, it's a model, you can think of it as really like this could be the data generating process, or you could think of it as something that gives you descriptives of the data, an AR parameter and a variance term. So I think it's an interesting thing to look at. There is some description of the comparison in the paper by Wang, but I'm sure other people will have a different take on it than in their paper.
Thank you. And talking about random walks, there's a short walk to the party that has just started and which will end at 6 o'clock. So just know that further questions will impede on the partying. But feel free to ask a few more questions, those who want to. Now.
Okay, may I ask a question?
Yeah.
Okay, so this is going back to the question of...
You have to put your mic very close to your mouth.
Sorry, my apologies.
There you are.
So if we can go back to slide 57.
What did you say?
57.
57.
Thank you. So I recall in reading in one of your papers, and I think it's also mentioned today, that these fit indices may not function in the same manner with Bayes as, let's say, BIC and other values.
Right.
So is it possible to test nested models with the Bayes approach? I mean, you're showing two different fit indices here, for example, and I'm wondering if we can really make a determination if one model is a better fit versus the other, if they're not.
You know, that topic
Nested.
is going to be covered in detail
Later on.
tomorrow morning.
Oh, okay.
So that's in the more technical section.
Thank you very much.
You'll get your fill of the answers there.
I appreciate
But
it.
thanks. All right, over here, final question.
Okay, so can I ask you about whether we can do joint modeling with a discrete time survival analysis with the method that we learned today? Yeah. Okay, thank you.